Hi folks, we're going to talk about vectors today. This will probably break up into a couple videos. Vectors are a big topic. If you've been introduced to vectors before, then great. This will hopefully add to that, clarify some of that. If you haven't seen vectors before, you will see vectors start appearing in a lot of applications. Those of you who go on to calculus, you do, I believe it's your third term of calculus, is even referred to as vector calculus. Those of you who do any physics, it's how most physics is done. Engineering is all done in vectors. Vectors become a big part of math and science in lots of ways. One of the side effects of that is there is a lot of different notation and vocabulary associated with vectors. So you'll see very quickly, even in this first page, several different notations for vectors, different symbology, and there's a lot of vocabulary associated with it as well. Luckily, the vocabulary is fairly standard through different disciplines, but depending on the particular ways the vectors are used in different disciplines, different notations can be handy. So if you do a lot of physics, you might be doing a lot of vectors in component form. If you're doing certain types of mathematics, you'll use them a lot in metric form. So it's just be aware going into this that there's a lot of seemingly overlapping notation. Why do we need these different ways to denote it? And it's just because they're used in so many applications in so many places. So try not to get too overwhelmed with that. The nice thing about vectors is not only how useful they are, is that a lot of the mechanics, particularly the mechanics we're going to talk about, are not terribly complex outside of the fact that it's a new set of vocabulary and a new set of notation. So, again, be careful of the new notation and new vocabulary, but try not to let that overwhelm you too much. Okay, getting into it, what is a vector? A vector is a quantity. They are quantities, which often immediately throws people off because these are individual quantities that have multiple parts to them. So it's a quantity that has both direction and magnitude associated with it. We often think of quantities as just being magnitudes, like how many bananas do you have? Well, that's a quantity of bananas. I have 6 bananas. That's a quantity. But when we talk about more complicated types of quantities, we often want that magnitude to be associated with a direction as well. For example, one of the big examples is velocity. When you're moving, you move at a particular speed, that's your magnitude, but you also move in a particular direction. And to understand how an object is moving, we need both of those information. How fast and in what direction, in what magnitude, in what direction. Even simple numbers we often think of as having a direction when we talk about the difference between positive numbers and negative numbers. The positive number 5 is 5 in the positive direction, while the number -7 has a magnitude of 7 but is in the negative direction. So you'll see a lot of overlap between how we work with numbers and how we work with vectors because in a lot of ways that overlap is very natural. Okay, so single quantities with both direction and magnitude. And speed and bearing, speed being a type of magnitude, bearing being a type of direction. We often visualize vectors as directed line segments like we have down here. And it doesn't have to be drawn on a grid. If we draw a directed line segment, that's just a line going in a particular direction at a particular length. And notice here, tail of the vector. Do notice when we're talking about a vector, how long it is matters, because we are trying to express, again, two qualities of this quantity. Its direction, the direction of the arrow, and its magnitude, how long the arrow is. So magnitude is defined by how long this directed line segment is, and its direction by the direction of the arrow, from some initial point to some terminal point at the tip of that arrow. So if we were to draw another vector trying to be the same direction, if I was to draw another directed line segment, not good at drawing today. That was supposed to be going in the same direction as this other vector. If it had the same direction and the same length, then those are the same vector. They don't actually have to be in the same location. You'll find as we go along, vectors don't have a set location. All they have is a magnitude and a direction. So if these are at the same angle, measured from somewhere, I'm going to measure it from standard position here. So if they have the same angle and are the same length, which these are about are, then they're the same vector. If a vector was going in the same direction, that's pretty close, was going in the same direction but had a different length, then it's a different vector, because it has a different magnitude even though the direction might be the same. Similarly, we could have a vector that's the same length as those, roughly, but pointed in a different direction makes it a different vector. Different magnitude at a different direction. Now notice I'm kind of implying that I'm taking this measurement of angle from some horizontal positive axis. You can take your angle measurement from anywhere you want as long as it's consistent through your system of vectors. Okay, get all that out of the way. Notation. I said there'll be a lot of notation. You will often see vectors denoted in boldface. That's mostly because it's easy to type a boldface letter. Sometimes you'll see them italicized because they are, again, that makes them look special. It highlights them and is easy to type or type into either old typewriters or computers. When working with vectors by hand, it's generally considered appropriate or best to have your vectors have, so vector V, have an arrow on top of them to denote that they are a vector. My arrows often just have a top on them. Sometimes people have both. So vector V, vector U, and again, you can have both parts of the arrow. You'll notice my notation tends to be just one part of the arrow. But if you're writing out vectors, you don't have the restriction of it being in typeface. So there's no reason to try to make, okay, that's a U, but my vectors are going to be a bold U, so I'm going to write them thicker. Don't do that. Just put an arrow on. You'll sometimes, if you have a vector going from point A to point B, have your vectors in this notation. The vector from A to B tells you what the initial point and the terminal point is. This sentence here, given an initial point of P and a terminal point of Q, we may denote the vector AB. I don't know why that says AB. It should really be the vector PQ, since that's the initial and terminal point that they labeled. So let's, for sake of argument, call this, oh, they already said the magnitude of there. So we're going to call this vector V. I'm going to put the little arrow on it so we all know it's a vector. So that's our vector V. We say a vector is written in standard position, similar to how we measure angles in standard position, if the origin, the original point, the initial point is at the origin of a coordinate system, and the angle is measured as an angle in standard position. So that gives us a vector in standard position. You will often see a vector in standard position denoted particularly by these endpoints. So if we go over this way some distance, in this case it's 4, and up this way some distance, in this case it's 2, that would make the coordinates of this point, notice the parentheses here, the coordinates of that point would be 4, 2. So we often will denote the vector, that's how I make my V's, sorry, some people get thrown off by them, I usually don't make them quite like that, I make my V's like this. So we'll denote the vector by this terminal point. So this terminal point is the point 4, 2. So we'll say this is a vector that goes over 4 and up 2. Notice the angled brackets. You can use greater than or less than symbols for that if you want. But a lot of software has particular symbols for it if you want to find them. But this is a vector in what's often referred to as position vector form, because it gives essentially the coordinates of the terminal point. But the big thing to express is that this is a vector that goes 4 units in the x direction and 2 units in the y direction. Now I've said x and y in quotes there because, it depends on what your coordinates are. If you call this the t-axis and this the w-axis, then it's 4 in the t direction and positive 2 in the w direction. But this is one of the more common ways to refer to a vector, particularly a vector that we are implying is in standard position. We'll talk about other ways to write a vector out as we go along. So that would be a fairly standard way to denote this vector V written in standard position. As I mentioned before, the magnitude of the vector, magnitude gives us a sense of the size or the scale of the vector. And it is the length of the vector from its initial to its terminal point, if we are putting it in a coordinate system. And we denote that by what will look like absolute value bars. Now I'm going to complain here a little bit. They are saying quite correctly that this is a standard notation for the magnitude of vector V. But you will often see, instead of the single bars, a more kind of an old-fashioned notation. You will see a double absolute value bars for magnitude. of, I suppose I can just say v, the arrow on top tells us it's a vector. So both of these notations mean essentially the same thing, but again, the double absolute value bars, the double bars, have fallen a little out of fashion because of typeface. But you'll see a lot of people use it, so some of your physics instructors especially may use it, some of your other math instructors may use it. So keep in mind. But there is a reason that it looks kind of like absolute value. That's essentially what absolute value does, is it gives us the scale of a number. How big is the number regardless of being positive or negative? Magnitude does the same thing. How big is the vector? What is its magnitude? Irrespective of its direction. And again, that can be with any notation for your vector. We could even say the magnitude of this vector for 2. So that's got kind of all our notation all squished together. These absolute value bars, either single or double. Again, I'm old-fashioned. You'll often see me do it with the double, but I'll try to kind of go back and forth so you get used to all the notation. Those absolute value bars are asking for the magnitude of this vector, and that would give us how long this vector is. That would give us its length or magnitude. Which again, magnitude is the length of the vector. So a couple mechanics that we want to have fairly quickly is we want to be able to turn points into a vector in standard position. So for example, we'll have an example down here in a second, but say, well, let's use the points here. This initial point is at 2, 2, and this terminal point looks like it's at 7, 4. Again, notice the parentheses on all these because they're just coordinates. So if we wanted to know what this vector would be if we put it in standard position, we essentially want to know how far is it in the x and how far is it in the y. Well, if we go from 2 to 7, we can figure out how far that is. From 2 to 7, take 7, I don't really want parentheses there. Take 7 minus 2, and, well, this distance has to be 5. And then from 2 up to 4, well, 4 minus 2, that's 2. So this vector goes over 5 and up 2. So, yeah, technically we have a formula for that, but we're really just taking the components, take the two x values, I keep trying to put parentheses places, take the ending x value, the terminal x value, subtract the initial x value. Notice they have x2 minus x1. Same thing. I'm just trying to be a little more explicit here. That 2 has to be the terminal and the initial. So it's end minus beginning. So end minus beginning. And then the terminal point for the y minus the initial point of the y. And this might look a little bit like slope, and it should, because that's kind of what slope does. Is it's the difference in the y's over the difference in the x's. This is just how far have you gone in each direction. And in this case, it's the 7 minus 2 and the 4 minus 2, giving us a position vector of 5, 2. So this vector, I'm going to call it W. W written as a position vector would be the vector 5, 2. It is a vector that goes 5 in the horizontal and 2 in the vertical. So it's just an example. If we have a point at 6, negative 5, so I'm going to plot that here, 6, negative 5, so down here, and that's an initial point, and then a terminal point at 2, negative 3, so 2, negative 3. So notice this vector is going in that direction. And I want to find the position vector. Well, essentially, we're going to pick this vector up, put its initial point at the origin, and then I want to go the same direction for the same length. So I need it to go the same distance this way, and I need it to go the same distance that way. Well, how far did we go that way? Well, we went from 6 to 2, so 2 minus 6. Notice end minus beginning. Because we're going in the negative direction, so this better end up being negative. So we go 4 in that direction. And then end minus beginning again, so negative 3 minus the negative 5. Or negative 3 plus 5, which is positive 2. So negative 4, positive 2. And that should be pretty clear on our graph. We're going back 4 and up 2. So over here, we're going to go back 4, 1, 2, 3, 4, and up 2, 1, 2. To get to the coordinates, the point, negative 4, 2. Which makes our vector, v, which they've called, well, they've called both v and pq, so this vector v is the vector negative 4, 2. Now, it's important to keep in mind, you might be asking, well, which vector is negative 4, 2? Is this vector negative 4, 2? Is that this vector? Or is it this vector? Well, again, those two vectors are at the same direction. They're pointing the same direction, and they have the same magnitude. So those two vectors are the same vector. One of them is expressed in standard position. The other one is expressed over here down in quadrant 4. But they're the same vector. This notation kind of expresses a standard position vector because it matches with the coordinates of the terminal point. But try not to lose sight of the fact that those are the same vector. So given any initial and terminal point, that makes it seem like it has to be in this location, but that's just the location of the event that we're saying occurs. But we find the vector, the description of the action that's occurring, by just taking the difference in those coordinates in the proper orientation. So building a vector, if we're given initial and terminal points in a coordinate system, tends to be fairly nice. Now we'll have to learn how to make a vector from other types of information, but we'll get there when we do. So, if we want to compute the magnitude and direction of a vector, given a vector, the nice thing is we already have the tools for that, though I'm going to be a little grumpy about how this is expressed. So, given a position vector, and again this is the vector 4, 2, so we might as well use that vector 4, 2. If we want to figure out how long this is, because that length is the magnitude of our vector, well, we already have a tool for that, and that tool is the Pythagorean theorem. Now, it's only sort of the Pythagorean theorem. The Pythagorean theorem would have this magnitude of v being squared. The reason that it's already solved with the square root is because we don't want that plus or minus. Magnitudes are always positive. So it is a slightly modified Pythagorean theorem because we only want the positive version, not the plus or minus. And that's why it's already been square rooted. But if we wanted the magnitude of this vector v, we just, like we would with Pythagorean theorem, the square root of 4 squared plus 2 squared, so the square root of 16 plus 4, it's the square root of 20, and hopefully you're in the habit of simplifying your radicals. The magnitude of that vector v would be 2 square root of 5. So it's just a Pythagorean theorem argument, which is nice. And again, magnitude is raw size, so it should always be positive. Direction, if we want that direction expressed as an angle, is essentially 4, 2 already kind of describes this direction almost in terms of a slope. You know, over 4 and up 2 describes a direction. But if we want that direction described in terms of an angle in standard position, we need some of our trig. Luckily, that's what we've been doing here. So, this bugs me, I'll tell you why in a second. So the relationship that's kind of the easiest one to grab, if we have this, the position vector giving us essentially the coordinates here, if we know how far we go over and up, tangent is a natural choice. So we know that the tangent of this angle has to be that vertical component over the horizontal component, our b over a. And this tangent formula will give us the direction of this vector. I really don't like that these notes then go, hey, here's our rule, the direction of the vector is theta equals the tan inverse of b over a, and it might seem trivial, but just like up here, doing the square root first restricts us to only getting the positive value, which is fine because magnitude's always positive. But down here, using the tan inverse restricts us to only getting values within the inverse of tangent, which means we're only between negative pi over 2 and pi over 2. We're only in quadrants 1 or 4. If we're headed in a different direction, like this vector down here, the tan inverse of 2 over negative 4 is going to give us an angle headed the wrong direction. And we have to know that, oh, well, we can get our other solutions by adding pi and going in the direction that we want to go. And that's fine. We're used to doing that when we solve. But if you say that the direction of the vector is the inverse tangent, then you're saying the direction is that restricted vector, which it's not necessarily. So that is me nitpicking, but I tend to be nitpicky. So we should be thinking that the tangent of the direction is that b over a, and then when we solve, we're going to get, sure, the tan inverse of b over a, but remember, we're also going to get all those extra half rotations from the period, and sometimes we need that because we need to be going into quadrant 2 or quadrant 3. Hopefully we'll see an example of that. I'm sure there are examples of that in your homework, so just be careful about assuming the answer you're getting from the tan inverse is correct. It might be pointed in the opposite direction that you want to go because of the nature of the tan inverse. So let's see an example. Determine the magnitude and direction of the vector PQ given that initial and terminal point P and Q. So it is a good habit to at least give yourself a drawing here. So our initial point P is at negative 8, 1. So negative 8, 1's about there. Negative 8, 1. And Q at negative 2, 5, negative 5. So negative 2, negative 5. They don't have to be in exactly the right place. We're just trying to get a sense. Negative 2, negative 5. So we're going in that direction. Okay, so I'm just gonna, no need to rename this vector PQ. Our x values are going from, again, it's end minus beginning, so -2 minus -8. And our y's are going from, again, end minus beginning, -5 minus 1. So the position vector form of our vector is going to be 6, it's really 6, -6? Okay, cool. 6, -6. Because, yeah, we go that way, 6, and then down that way, -6, so 6, -6. Great. So if we wanted to draw it in position vector form, it's going to terminate at the point 6, -6, and our vector PQ has this position vector form 6, -6. Okay, so its magnitude. If we want the magnitude of PQ, we know it's got to be the square root of 6 squared plus -6 quantity squared, which is the square root of 36 plus 36, which is the square root of 72, which is, what, 3 square root of 8, which is 6 square root of 2. I know that might take you a little longer, but you know how to simplify radicals. If not, practice it. So, great, we have a magnitude. That's how long this vector is. If this was an object moving, that would be its speed. If this is a force, that's how hard it's pushing, whatever this happens to be. Now, we also want a direction. So, our direction, the tangent of our angle that we're headed out in standard position, again, it's going to be b over a. So essentially we're trying to find this angle. So the tangent of our angle is going to be -6 over 6. So the tangent of our angle is -1. Now, I don't want to belabor this point too much, but notice if our vector was pointed the opposite direction, if it had been pointing this way instead, then those coordinates would be -6, 6. So the tangent of our angle would be 6 over -6. We'd still be looking at the tan inverse of -1. The tangent can't tell the difference between this angle and this angle. We have to know which one we want. Now, the nice thing is, when we take the tan inverse here, tan inverse of -1 is going to naturally give us the -π/4, or -45 degrees if we're in degree mode. So it's going to give us this -45 degrees. But we have to know that it's also suggesting maybe the 3π/4 or the 135 degrees. And we have to go, no, I want the one pointed into quadrant 4, so we want this one. If we wanted the one going this way, we'd have to use the other one. So be careful about that. Whether we're expressing these in degrees or radians is really up to you or the question. Make sure you read the question carefully to know whether it wants the direction in radians or degrees, but either way. So we have a magnitude of 6 square root of 2 and a direction of -π/4 radians. Okay. Now, since vectors are quantities, again, they're quantities just like numbers. They're just quantities that have now multiple pieces to them. They have both direction and magnitude. We can do a lot of the things that we can do with normal numbers with vectors. We can add them, we can subtract them, we can multiply them. We can't quite divide them. Division is weird, but we'll talk about that later. So we can do a lot of the things we can do with numbers with vectors. And one of the nice things is, if we have two vectors that we want to add together, say this is vector v and this is vector u, we can add vectors visually by kind of moving them around so that we have one vector and then the other. And that's what's essentially happening here. But I'm going to grab this vector. Remember, vectors don't have position, so this is the same vector no matter where we put it. It has the same direction, it's at the same angle, and the same magnitude no matter where it's located. So I can, if we want to, place it so that the initial point of u is at the terminal point of v. This is often called the head-to-tail method. The tail of this vector is pushed onto the head of that vector. And then when we add them together, we can visually represent their sum by the vector that stretches. This one happens to be almost purely horizontal, which is fun, but not always the case. The vector that goes from the initial point of one vector to the terminal point of the other. So this new vector is the vector that results from v plus w. Sorry, v plus u. That makes a new vector. I'm going to call that one w because I want to. So we can add vectors visually by kind of moving them around and saying, hey, we're going to take this vector plus that vector. Now, we could have done that in the other orientation, and it still should work. If we did it in the other orientation, put the u and then the v, notice this vector w should still fit in that same spot. Because like addition for normal numbers, addition for vectors is commutative. We can add them in any order that we want, just depending on how we arrange them. Now, if you want to subtract two vectors, lost my tool. If we want to subtract two vectors, we can essentially do the same thing if we want to subtract these two, except that we take, I'm going to grab my vector v here. If we've got this vector u here, well, I'm changing my order here. Let me restart that so I can change the order. So, subtraction. If we want to find the vector v minus, or subtracted from the vector u, so u minus v, and we have a vector u, this is u, and we have some other vector v, and we want to subtract them, well, it might help to remember that subtraction's not really a thing. There really is no subtraction. There's only the addition of negatives. So what we're really talking about isn't subtracting v, we're really talking about adding the opposite of v. Well, what does it mean to be negative v when we're talking about vectors? Well, it just means that you're a vector of the same magnitude pointed in the opposite direction. So instead of going from P to Q, the opposite goes from Q to P. So if we wanted to subtract these two vectors, turn v into the opposite of v and do the same head to tail. Kind of move all my little pieces. And then the resultant vector is still the vector that goes from the initial point of the first one to the terminal point of the last one. So that's going to be our new vector, u minus v, or u plus negative v if you prefer. So having this very visual way to add and subtract vectors together is handy and nice when we do diagrams, particularly force diagrams, trying to understand the effects of different forces on objects. And actually, in the olden days, it used to be very common to draw out all these vectors very, very carefully and sketch out their angles very precisely, and then be adding and subtracting our vectors together by drawing that resultant and measuring its magnitude very accurately and measuring its angle very accurately to perform a lot of the mechanics, particularly before we had, a lot of computers and calculators to handle some of the trig that we now take for granted. So while this is a very common and nice way to visualize what's happening with our vectors, we also want ways to add and subtract vectors that are a little more concrete. The nice thing is, if we have a vector in component form or position form, this form is often called a version of component form because it has the horizontal and vertical components. So if we had a vector like 6, 2, and we wanted to add that vector to 4, 5, the nice thing is we can perform this vector addition in a very straightforward way just by adding like components. So this one goes 6 in the horizontal, we're adding something that goes 4 in the horizontal, so together, well, guess what they're going to do together? Together they're going to go 10 in the horizontal. This one goes 2 in the vertical, this one goes 5 in the vertical, so if we add them together, they're going to go 7 in the vertical. So this kind of position vector, this coordinate vector form is very nice for adding. It looks a little complicated here because of all the sub notation, but it's just take the x's, add them together, take the y's, add those together, and we have our new resultant vector. And it matches up exactly what we would get if we did it with the directed line segments, but is cleaner because we have those numerical values. So adding vectors in this kind of position vector or component vector form is very, very, very handy. Even subtracting it, if we had the vector, say, -2, 3, and wanted to subtract the vector 6, -5, for whatever reason, then that result we're going to get the same way. Just being careful that we're performing a subtraction. So -2 minus that 6, and then 3, careful here, 3 minus this -5, so 3 minus that -5, and we can subtract those vectors. So -8 and +8, that's fine. So adding and subtracting vectors in this kind of component form or this position vector form is very, very handy, very, very nice, very, very quick. So keep that in mind later on when you have vectors defined based on angles and based on magnitudes, and you want to try to add or subtract them, converting them into this kind of position vector form can be very handy and often necessary. So keep that in mind. How are we doing on time? 5 minutes. Okay. I think these last two will be great, and then we'll put everything else on the second video. Okay, so we want to add these two vectors and subtract these two vectors, and we want to do it both geometrically and analytically. So we want to do it visually with the directed line segments, and also do it just numerically, analytically. So this vector u in standard position would be 3, 2, so over 3, or 3, negative 2, sorry. So over 3, down 2, so that's our vector u. I'm going to zoom this in a bit. Good. That's better. Now our vector v, if we wanted to put it in standard form, would be, okay, negative 1, 4, negative 1, 4, we put it there. But since we're going to add them together, I want to use that head to tail method. So I'm going to take this vector v and put it at the terminal point of u. So from here, we're going to go negative 1 plus 1, 2, 3, 4. So we're going to place our vector v there instead, so we can perform that addition. So then our sum is going to go from the initial point of the first vector to the terminal point of the second vector. And this orange one, that result, that is our u plus v. And it looks like it's 2, 2. It looks like it goes over 2 and up 2. We'll see if that matches with our analysis here in a second. Well, let's just do that right now. So we've got u plus v. So our u is 3, negative 2, plus our v, negative 1, 4. So if we want to add those, we're just going to take the 3 plus negative 1 and the negative 2 plus 4, and yeah, we're going to get 2, 2. Same vector. Now for the subtraction, we're going to start with that same vector u. So down 2 over 4, so it's going to end there again. So that's our vector u. But we don't quite want v. We want v's opposite. So we want something going in the same direction, or sorry, the same magnitude as v, but in the opposite direction. So I'm going to first list out, well, what's the opposite of v? Well, instead of going to the left 1 and up 4, it's got to go to the right 1 and down 4. So instead of going up this way, it's going to go over 1, down 1, 2, 3, 4. It's going to put us down here. So that's v's opposite. So that's going to give us a result that goes from, again, the initial point of 1 to the terminal point of the second. And that's going to be our new vector u minus v. And you can think of these sums and differences if you're talking about velocities. If you got like the speed of the, or the velocity of the airplane plus the velocity of the wind, those things are going to affect each other. So the speed and the direction of the wind and the speed and the direction of the plane are going to add together to give you a result. How fast is the plane actually going to go, and in what direction is it going to go? If you've got a force going in one direction but it's resisted by friction, that force is going to be, or is going to have the friction subtracted from it. So those vectors are going to subtract. So these have lots and lots of very, very solid applications in many, many fields. So if we want to perform the subtraction, make sure we get an answer that matches that, we're going to be talking about 3, negative 2, and this time subtract negative 1, 4. And again, you can think of this almost like distribution. We'll talk more about that in the next video. If these were, polynomials we were subtracting, we'd have to subtract all the coordinates. It's the same kind of thing. So we'd get 3 minus negative 1, and then negative 2 minus 4. So that looks like 4, negative 6. And this thing looks like it goes, well, down, oh, sorry, wait a minute. Yeah, 4, negative 6. Looks like it goes down 1, 2, 3, 4, 5, 6. So that's the negative 6. But it looks like it goes over 1, 2, 3, 4, 5. 3, negative 2, negative 1, 4. I wonder why that is. 3 minus negative 1 is 4. Oh, why am I going over 4 here? Yep, I did my u as negative 2, or it's 4, negative 2, not 3, negative 2. And nobody yelled at me. That's a nice reason to do it twice. So this vector should be can't do it. This vector should be here instead, and then this vector should be there. So our actual resultant vector should have been here. Well, nice. It's always nice to make little mistakes and try to figure out where they come from. That's fun. Okay, so if we get our proper vector, the 3, negative 2, and then put in the opposite of v, so that's over 1, down 4, then we'll get our proper resultant vector, 4, negative 6. Cool. So that's going to be our u minus v. Cool, cool. Okay, so practice that. Go off and practice that. And we'll talk about multiplication in our next video. I tried to put all this in one video and I made a mess. So we'll talk about multiplication in our next video. But one of the previews for that, you might have recognized over your kind of career that we have different notations for multiplication that are commonly used. We've got this juxtaposition notation where we just put two things next to each other, and that's multiplication somehow. In some point in school, you used a dot to do multiplication. And then usually really early in school, you used this cross. It is a cross, not an X, so it's use this cross to imply multiplication. And it might have bugged you, well, why are there three different notations for multiplication? Well, you're about to find out why. Because in vectors, these three things mean different things. This is scalar multiplication. This is appropriately called a dot product. And this is called a cross product. And when we're talking about vectors, these mean three different things and give us three different types of results. Those results just happen to match up when you're talking about numbers. So if you're just talking about good old-fashioned numbers, these three things are interchangeable. But as soon as we're talking about true vectors, they're different objects. They're different actions. So we'll talk about scalar multiplication and dot product a little bit here. Cross product, we generally need 3 dimensions instead of 2, so you'll talk about cross products usually when you get into later physics or Calc 3. So we'll talk at least about these two in our next video.